So here's our bell work. Solve these two equations. These are both one-steppers. And so we only need one principle of equality to solve them. Starting with this number 1 here, we don't want 6 m's right here. We'd really like just to be phantom 1 m's. So we got to divide both sides by 6. Actually, so I in the last lesson I kind of showed it like this with division. Some students, I think, prefer to show it like this with division like this, divide by 6. And that's okay if you do, just as long as you do it to both sides, right? Because it is a principle of equality. So 6 divided by 6, there's our phantom 1. And then negative 66 divided by 6, negative 11. Okay, and then we can check 6 times negative 11. You could replace the negative 11 in there. We're just checking for truthfulness now. 6 times negative 11 does actually equal negative 66. So that checks off. And then number 2 is pretty much exactly the same problem. I'll show the division differently, just like we did last time. So again, we don't want negative 2x's. We're just like this phantom 1x. So how do we make a negative 2 a 1? Use the division principle of equality. But whatever you do to one side, then you got to do to the other side. So there's our phantom 1. 4 divided by negative 2, negative 2. And again, that checks off. Negative 2 times negative 2 does actually equal positive 4 there. So that would be a true statement. Here's our objective for the day then. I can solve equations that require 2 principles of equality to solve. So just like we talked about during the last lesson. Now, where last lesson only required 1 principle of equality, now we're going to need 2. So just as a quick review, what is a solution? Remember, a solution is going to make the original equation a true statement. That original statement that's an equation, it needs to make it true, which is what we just saw in the bell work there. So remember, if you find that x equals 5, then whatever the equation is, like, I don't know, 2x plus 10 equals 20, something like this. And when you go back to replace the x with 5, it needs to make the equation true. If it makes it false, then you know that you've made a mistake somewhere. This would not be the solution. I mean, this one makes it true, but if it didn't, if you found that it made it a false statement, you'd have to go back and look and see where a mistake was made. Sometimes that's in entering the value into the calculator, or it's pushing the wrong button. Sometimes it's maybe you used the wrong principle of equality. You have to look back and find out. So solving 2-step equations. Again, it's going to require 2 of these. Now do remember what we talked about last time, addition and subtraction. These are to make zeros. And this is pretty crucial, right? So if you see a value that's being added or subtracted, you need to make that value 0 yourself. Force it to be 0. Take control of the problem. And don't let it take control of you, because if you don't, then sometimes it does. And then for multiplication and division, this is to make 1s. But not just to make 1s. This is specifically to make the coefficient 1s. That's the coefficient. And from the last lesson, we saw 2 examples of one for multiplication, 1 for division, where we forced those coefficients to be 1s. Now, just so we understand, generally speaking, although it doesn't have to always be this way, we usually use addition and subtraction principles of equality. So we force zeros to happen first, and then we force 1s to happen next. And do remember that these principles of equality are maintaining equality. So while it may look something different in the beginning, like we saw there in the last example, 2x plus 10, if this equals 20, this is what it looks like in the beginning. In the end, after using these principles of equality, it's not that we've changed the final value of the equation. Like, it doesn't mean that we've changed the equality part of it. We've only changed the way that it looked until you'd get to x equals 5, which would be a true statement, okay? X equals 5 would be the solution, because it would make the original equation a true statement, okay? But again, we generally make zeros first, and then we make 1s. Here's why. Is because right now I got 2x plus 18 equals 10, and what I would really like is just to have the 2x equal something. I don't want anything added or subtracted to the x's. In 7th grade, it's possible they may have said something like, this is when you isolate the variable. Okay, whatever the case is, I just want the x's by themselves, which is another way to say that you're isolating them, okay? All 2 of these x's. I don't want that plus 18 there. So I need to make it go away. And to make it go away, you make it be a 0. That way we can ignore it, just like we do people, unfortunately. So I'm going to have to take that positive 18, and then I subtract 18. But the principle of equality says if you do it to one side, you got to do it to the other side as well, okay? So what happens here is I do drop the 2x because I wasn't operating with it. And then I got the 18 minus 18, which is 0. Remember, that's a circle, but it's a 0, actually. I zeroed both of those out, which is what I wanted to do. That was kind of the goal here in the first step. And then you can use the calculator to do 10 minus 18, which I highly recommend because the calculator doesn't usually make mistakes. But that'd be negative 8 right there, okay? So now we have this equation, which is very similar to the two that we did in the bell work. And the last thing I want here is a phantom 1x. I don't want 2x, I just want 1. So I'm going to divide both sides by the coefficient 2. See that 2 divided by 2 makes a 1. It's just a phantom 1 in the next part. And then negative 8 divided by 2 would be negative 4, okay? Now, just like we did last time, I'm going to check this one. So 2x plus 18, this would equal 10. But right now, I think that x equals negative 4. So I replace x with negative 4, and I check for truthfulness. So there's my question mark over the equal sign. Because I don't know if this will make it true. I mean, I did my principles of equality. It should make it true, but I want to make sure that it is. So 2 times negative 4 is negative 8. Then we'd have plus 18 equals 10. And one more step here for us. Negative 8 plus 18, that'd be 10. So that means 10 does equal 10. And as of now, that's true. It should always be true, which is very nice. It was true yesterday, it's true today, it should be true tomorrow and forever. And since that is the case, I see that that's true. That means that x equals negative 4 is the actual solution to our original equation. I really do hope adding an extra step here doesn't make a huge difference. And for those of you wondering, yeah, you did do 2-steppers in 7th grade, but again, we're just kind of reviewing this stuff to make sure you have it down before we expand these problems a little bit bigger. All right, here's another one. And now the x's are on the right side of the equal sign. No problem. I just want to isolate them so that they're by themselves. So the first thing I'm going to do here is I don't want that plus 4 there. I do not want it there. I would like this negative 3x to just be by itself. Okay. So to do that, remember, I kind of set it up like this. I know some teachers, like some 7th grade teachers, just teach it where you got this line right here. I like this line right here so that I know that I'm operating with these two values, okay? So the positive 4 has to be zeroed out. And how am I going to do that? I'm going to just subtract 4. Boom. There you go. But if you do it to one side, please make sure to do it to the other side as well. So that's going to zero that out just like we wanted. It will drop my negative 3x. But now I got negative 14 minus 4. Now, I know some of you can do that in your head. Just be careful to make sure you get your sign correct. For those of you that don't like to do it in your head, just do it on the calculator. That's what it's for. So negative 14 minus 4 would be negative 18. And this will equal now negative 3. So once again, this principle of equality, I've only changed the look of this equation. I haven't really changed its equalness. Okay, so it's still equal. I just changed the way that this looks. And I'm going to continue to do that now with a division principle of equality because I don't like that negative 3 being the coefficient of x. I'd like it to be a phantom 1. So how do I make a negative 3 1? Just divide it by itself. So divide that by negative 3. But if you do it to one side, you got to do the other side. Again, whether you show this in fraction form like I've been doing or whether you use the division sign here is up to you. But some students told me they prefer to see it like this, and that's fine. There's my phantom 1. So now I'm left with just the x. And this will equal now negative 18 divided by negative 3. Put that in the calculator, you get 6. All right, so right now I think x is 6. And that seems like it should be good. Just looking at the principles of equality I've used. But I am going to check. So negative 14 equals negative 3x plus 4. But I now think that x is 6. So I replace the x with 6. And see what happens, okay? Now if because there's no operations here on the left, so I'm not really doing anything with that negative 14. Although later on there could be, okay? Right now, I'm doing the order of operations, or performing the order of operations on the right side of this equation. Some of you would just plug the whole thing into a calculator and be done. But I want to show you something that happens when we work this through. So negative 3 times 6 is negative 18. And I'm purposely using red because where do we see negative 18 in our work? Right here, okay? After we subtracted 4, right? So now this right side of the equation would read negative 18 plus 4. And then would say, look, take negative 18 and add 4. What do you get? Well, that's negative 14 right there. And see how this kind of backtracks right here, right? Here we divided by 3, here we multiplied by 3 to get this negative 18 and negative 18. And then we added 4, whereas up here we would have subtracted 4 to get back to this negative 14. See that? So it's kind of like a road map here, but whatever the case is, this is true. Negative 14 actually does equal negative 14, which means that this is the solution to the original equation. It's kind of a unique scenario because we see this from time to time on tests or quizzes, and students tend to get this one wrong. In fact, I'm not completely sure how that happens. They'll just write g equals 17 like there's no negative sign there, but there is. And what's happening to this g right now? Well, it's got a coefficient. You just can't see it. It's a 1, but it's not actually 1, it's negative 1, okay, because it's got this negative sign. Now remember, we don't want negative coefficients of our variables. We would just like the variable to be by itself, which indicates that it's a positive 1 coefficient. So how do I make a negative 1 into a positive 1 coefficient? Just divide it by itself. But if you do it to one side, you got to do the other side right there. So that becomes a phantom 1, just like we're showing right here. And 17 divided by negative 1. Again, just if you need to put that in the calculator, that shouldn't be something you feel ashamed about. But if you do, use it anyways because it will help. Now we can check, right? The original equation right here was negative g equals 17. And right now I don't know if this is going to make it true, but if I replace g with negative 17, what's going to happen? And even your calculator will tell you what will happen right here. I'm going to put this in parentheses on purpose. But if you type this into the calculator, it will punch out for you 17. And yes, 17 does actually equal 17. That's a true statement. So now you know that g equals negative 17 is the solution. Now that's a lot of work, you may say, just to prove that g is negative 17. That's okay, I don't mind doing it. And I hope that you don't either, because it's a good way to make sure that your answers are correct. Now the work up here, though, some of you would not show that. You just pretty much transfer this negative to the 17. That's okay. It's essentially the same thing. You've just done it a little bit differently. And if you understand that shortcut, that's fine too. So this brings us into what the heck is a fraction? Well, fractions and equations look like this, which we kind of saw a problem like this last time. But a fraction, at least the fraction line itself, represents division. Okay? Remember that it's division here, okay? So when we see w and this divided by 9, it's kind of like a division sign, and some students like to show it like this as well. If you prefer to see it as division, like this, okay? Now, why is this important? Because it's kind of like fraction multiplication right here, which you did do a lot of, I think, in 7th grade. And so we don't want this divide by 9 with a w. Remember, this is kind of our goal here. We would just like the w to be by itself. W equals something that would make this a true statement. So I don't want that divided by negative 9. So what I'm going to have to do is, and we saw this last time, I would multiply by negative 9. Now, some students even like to see this as negative 9 over 1, because what this allows me then to do is to take these negative 9s and cross-simplify them. And then you'd have w divided by 1, which is the identity property for division. And that really just gives me 1w right there. Now, I haven't finished this because, remember, whatever you do to one side, you got to do the other side. So that's multiplied by negative 9 over here as well, which when you do that, you will get positive 36. You can put that in the calculator to make sure. And then, again, just to make sure, you could say, well, what is 36 divided by negative 9? Yeah, it's negative 4. That's true. So this value of W will give us a true statement here, okay? Which is the whole point of this. And I'll emphasize this again, even though we talked about it last time. This is only one value, there's only one value that will make this true, and that's this one. If you found any other value and try to put it in here, it will give you a false statement. It will always be false unless you put a 36 in there. All right, here we go. This is a two-step equation. Now we look at that x divided by 4. There's a couple different ways to look at it, by the way. And I'll show you both and then solve both, okay? But first off, I don't want that minus 7 there. It's got to go. In fact, as a term, that would be considered negative 7. How do I make a negative 7 a 0? Just add 7 to itself. All right. So there's plus 7, but if I add it to one side, I got to add to the other side like this, okay? So that's going to zero that out just like I wanted. And then I will drop my x over 4, or you could say x divided by 4 if you'd like. Negative 2 plus 7 is 5. That's positive 5 right there, okay? Now I said I'd do this two ways. Just choose the way that you like the best, although in the future we may use a different way. Okay, so I'm going to solve this as though nothing's changed. So we're going to just make this x over 4 equals 5. But over here, I'm going to solve it. I'm going to show it a little differently because the x right now has a coefficient, not just of 1 right here, but we would actually say 1/4. So that's why I'm showing the 1 right there, that phantom 1. Some students like to see this as 1/4 x equals 5. And if that's you, then you're going to prefer the second method, okay? I'm going to solve this one like we did, that last problem. If you like that method, then ignore what I'm doing here, although it may be useful in the future. We'll find out, okay? But to solve this here on the left, all I would need to do is multiply both sides by 4, okay? And some people would say, well, they're inverse operations. Multiplication is inverse with division, and so they kind of undo each other, if you will. For me, I just know that makes a phantom 1, which is the whole point here, because now x will equal 5 times 4 is 20, okay? Now, I'm going to give the same answer for this other way, but again, we're going to use one principle of equality to solve this, even though there's a fraction right here. Some of you may choose to do that in 2 steps. But, just as usual, the only thing I have to do at this point, and it is essentially the same, is to divide both sides by the coefficient, because anything divided by itself is 1, no matter if it's negative, positive, decimal, or fraction. Anything divided by itself is 1, so 1/4, if I take it and divide it by 1/4, I will get a 1 right here. And that, again, that's kind of the whole point here. That's going to give me x equals, but remember, if you do it to one side, you're going to have to do it to the other side as well. So there's 5 divided by 1/4. And while some of you are thinking, well, I got to do some division with fractions, no, you don't. The calculator will do it for you, and it will tell you right here that 5 divided by 1/4 is 20. So this is the same answer for both methods right here, okay? Now, which method do you like the best? I don't know. And frankly, I don't really care as long as you have one that you prefer and can use, all right? Now, let's go back and check. So I got x divided by 4 minus 7. This should equal negative 2. So I replace my x with the value that we found for x 2 times, by the way, 20. And I will check for truthfulness. There's my question mark. Now this time, instead of working that through with the order of operations, I'm just going to plug this into the calculator. So even using the n over d button here, n over d, 20 over 4, get out of the fraction, minus 7, enter. And yes, just as expected, that results in negative 2 equals negative 2, which is a true statement, okay? So since it's true, now I can go back, and I feel a lot better about boxing in my answer, no matter which method I used. So right here, we got another fraction. This one is kind of mimicking that last problem. And again, the first thing I want to do is isolate my x's, even though that's only a fifth of an x. So I got x over 5. That's what I would like to just drop. I don't want that plus 13 there, so I'm going to have to zero that out with minus 13. So, but if I do it to one side, got to do the other side. So that will zero that out, just as we wanted. 24 minus 13 is going to give us 11. So I got 11 equals x divided by 5. And I want to get rid of that divide by 5, so I'm just going to multiply both sides by 5, okay? That will become a phantom 1, which leaves me with just the x equals 5 times 11 is 55. Okay, now you can check. You can say, well, what happens, and I'll just kind of take a little bit of a shortcut here, but if I replace the x up here with 55, will that give me a true statement? Well, just put it in the calculator and be done with it, okay? So here we go, 55 over 5, and then plus 13, enter, boom, 24. And it does actually equal 24, which is a true statement, which means that 55 is the actual solution here. So 24 equals x plus 3 all over 5, and then plus 9. So I kind of want to isolate the fraction on this one. I don't want that plus 9 right there. So I'm going to get rid of it. And by get rid of it, I mean zero it out. So I'm going to subtract 9 from both sides. This one, by the way, it looks like it's going to require 3 principles of equality, which we'll show. So that will zero that out just like we want. 24 minus 9 is going to give me 15, which now equals what I have here on the right. Yeah, we were able to just drop this. And so now what would I do? Well, I don't want that divided by 5. I would just like the x plus 3 there. In fact, most people don't like this fraction stuff. So I'm treating it like it was just an x right here, like we did on the last problem. And to get rid of that 5, then I'd have to multiply this by 5. But if you multiply one side by 5, you got to multiply both by 5, okay? So that makes that a phantom 1. I'm left now with just the x plus 3, which was kind of the point there, which equals 15 times 5 is going to give me 75. Put that in the calculator, you'll get 75, okay? Now you can see we're kind of chopping away at this, right? We got rid of the plus 9, and then we got rid of the divide by 5. Now I've got this plus 3. I got to get rid of it by subtracting 3, not just from one side, but both sides to zero that out, which it does. Now leaves me with x equals, looks like 72. Now again, we can go back, you can rewrite the equation if you'd like, but I do want to check to make sure this is true. So I'm going to replace the x up there with 72. I'm going to type this into the calculator. When I push enter, I should get 24, okay? So I'm going to push the fraction button first, type in 72 plus 3, then go down to the denominator, 5. Now get out of the fraction, and then push plus 9, enter. Boom, it does equal 24, which means that we have solved this correctly, and x equals 72 is the actual solution for this equation. Again, any other value won't work for this. Only x equals 72 will work. A wise man once said, 600 reduced by twice my age is 458. Write an equation that represents this situation. We'll use a to represent the man's age. Okay, lowercase a, I guess, whatever. So 600 reduced by twice my age. Okay, so that means that you'd have to start here with the 600, and then you will reduce it. Okay, so it says reduce, which indicates subtraction here. Now twice would be 2 times, and then remember his age is a, so 2 times the age, I'm just going to show that it's 2a. You can put the multiplication between it, I believe, if you'd like. But then it says is, that by the way would be an equal sign, well, 458. So there's my 458. So this is the equation that we're looking at. 600 minus 2a equals 458. And then we have an equation that is pretty much like the other ones that we've been solving. So the first thing I'm going to do is get rid of that 600. Now, I think this is the first time we're going to see this part, but that's going to zero out. And I'm going to do 458 minus 600 on my calculator. That gives me negative 142. But here's where a mistake happens, okay? So we do need to drop this 2a, but it's not actually just 2a. It's got that negative sign out in front, right, which makes the term itself a negative. So I actually end up with negative 2a equals negative 142, which now I would divide both sides by negative 2 to solve. So divide here by negative 2, divide by negative 2, make that a phantom 1a. So a now equals, looks like 71. Now, no need to label this because it didn't say if this was years or months, but I'm just going to leave it at 71. You could write age if you'd like, but on Canvas, you're just going to need that 71. But would that make a true statement? Well, that's when we go back and check, right? So put a 71 there in for A. And then I can type that into the calculator. 600 minus 2 times 71, enter, 458. Yep, that would make the old man's statement true. Boom. This last one here, Ed was going to sell all of his stamp collection to buy a video game. After selling half of them, he changed his mind. He then bought 17 more. He now has 42 stamps. Write an equation where X represents his starting stamp collection. Okay. And then I guess we'll solve it even though it didn't ask us to. But in any case, so, and keep in mind when you're reading these types of word problems, it may take several readings to really understand what it takes. Some students have told me they've had to read it 10 to 15 times to do it. Now that's an extreme case. Most of the time it's 4 or 5. And that's an expectation you're probably going to need in order to solve these, okay? But Ed was going to sell all his stamp collection. He sold half of them. So here's what I don't know. X needs to represent his starting stamp collection. So X is the starting number of stamps. Okay. And so first off, he takes his stamp collection and he sells, where did it say, half of them. Okay, so that's, I'm going to multiply that by 1/2 right here. Some students actually would show this as X and then divide by 2. It's up to you. I'm going to show it like this. I think this is a little bit more specific, but some people like it like that, and that's okay. So he's going to sell half the collection, but then he didn't like to. He didn't want to do that anymore. So you're going to have to buy 17 more. Buy means he's going to bring back, so that'd be adding 17 more stamps to his collection. Now in the end, because this is what he has now, so this is what it will equal, he ends up with 42 stamps, okay? So 1/2 X plus 17 equals 42. This would be the equation you'd need. Again, you could have shown it like this, so I'll show both ways here, where none of this stuff really changes. The only difference perhaps is where you have divide by 2 like this, okay? Now I'm going to solve it with one on the left though. So that means that I'd have to zero out the 17 there, so minus 17, but if you do it to one side, you got to do it the other side. So that's going to make 25 there. And then I'll bring down my 1/2 X. Then here, I would say divide both sides by 1/2. And this will finalize X, because that becomes a phantom 1 here. So now X now equals, looks like 50. Okay, so it appears, and yeah, I'll label this, even though I think on the computers you don't have to. I'll label it, since I'm doing it by hand, 50 stamps. Okay, so would that work? Well, 1/2 times 50 is 25. Remember, we should be seeing this as we go backwards. And then plus 17, yeah, that's 42. It works. Our objective, I can solve equations that require 2 principles of equality to solve, even though we did see one with 3.